there, it's Shannon Matchick-Myers, and today we're going to be checking out differentiation and integration of vector-valued functions. So I thought a good idea would be for us to warm up by practicing just some basic derivatives with respect to the independent variable. I think I used x for all of these. And so why don't you pause the movie and warm it up. And we've got two warm-ups, one for differentiation and one for integration. And then we'll get started. All right? On your mark, get set, go! I know you can do it. Woo! All right, let's see how you did. So we're differentiating with respect to x. So evaluating d dx of both sides. We will get on the left dy dx, or y prime. And on the right side, let's see what we have going on. You can either do it as a quotient rule, or you can do it as a product rule if you change the denominator into a negative exponent. I'm just going to use the quotient rule. So when we differentiate the numerator, we'll end up getting, remember the chain rule, so we'll have 2 times a something to the 1 power, and then times the derivative with respect to x of our something. And what was that something? Beautiful. It was sine at 3x. So we still need to differentiate sine at 3x. And then this whole thing will be multiplied to x to the 1/2. Subtracting from that, we'll have sine squared at 3x, and then times, what's our derivative going to be? It's going to be 1/2 x to the negative 1/2, and that's going to be all over root x squared. All right, so continuing, we'll get dy dx is equal to. So continuing with that derivative, we'll have 2 times sine at 3x. Applying the chain rule again, I'm going to do it a little faster. The derivative of the numerator is 3, and then when we differentiate sine of something, we get cosine of that something. That something was 3x. Cool, cool? All right, and this is all still multiplied to x to the 1/2. And now this one will be minus, I'll just clean it up a little, 1/2 x, I can't write today, x to the negative 1/2 times sine squared at 3x, all over x. Okay, so why don't we go ahead and factor out what we can so we can make this pretty. So we're going to get dy dx. Let's see. We'll have a factor of 1/2 and x to the negative 1/2. And then we have a factor of sine at 3x. And now, what does the first one need? I think we'll need a 4 to balance out that 1/2. We took care of our sine at 3x. We also need a 3, right? So I'm just going to erase that 4 and put 12, because we would have had 6, but we're multiplying by 1/2. And then we're going to have, as far as our x goes, it'll be x to the 1 power, because x to the negative 1/2 times x to the 1 is x to the positive 1/2. And then we'll have our cosine at 3x. Now, let's see, we have our 1/2 for the second term. We have our x to the negative 1/2, so we're just going to be subtracting 1 factor of sine at 3x all over x. And then we'll get dy dx will be we'll be able to drop down that x to the negative 1/2 and combine it. So I believe we'll end up with sine at 3x times 12x times cosine at 3x minus sine at 3x all over 2x to the, so x to the 1/2 times 1 is going to be x to the 3/2. Cool, cool? All right, so we're done with that first one. Sorry, I didn't leave very much space for that. Actually, I want to be able to see this problem better. Okay, so next up, we have f at x is equal to x times e to the negative 2x. So differentiating both sides with respect to x. On the left side, what are we going to get? Beautiful. F prime at x. And then remember, overall, we have a product rule going on. So this is going to be equal to the derivative of the first term, which is 1, times the second term, which is e. Whoops, I don't need it to be that high, I'm sorry. So derivative of the first term, which is 1, times the second term, which is e to the negative 2x, plus the first term, which was x, times the derivative of the second term. Don't forget to differentiate the angle, right? So we'll get negative 2e to the negative 2x. And now cleaning this up, we'll get f prime at x is equal to, let's see, e to the negative 2x times 1 minus 2x. And you might want to, I don't know, if you could also write it as 1 minus 2x all over e to the negative 2x. Both results would be fine. How are we doing so far? You remember this cool stuff? Gotta love that Calc 1. All right, so our next derivative is, it looks a little bit complicated, but hey, why don't we do some properties of logs to rewrite this first term at least. So we'll get y is equal to 2/3, it's our power rule, right, times natural log at 5x minus natural log at e raised to the x squared, and then minus 6x to the negative 1 minus arctangent at 3x cubed. So I haven't differentiated at all, I've just rewritten it to be prettier. So differentiating, remember we can apply that derivative to each one of these terms because it is a linear operator. So for our first one, this one will just be what, dy dx or y prime. I'll write y prime this time. And that's going to equal to 2/3 times, well, we'll have 5 over 5x for the first one. And then I'm going to write this again. So that's been differentiated. This will be the derivative with respect to x. When you're raising when you're evaluating the natural log of the natural exponential, you're just going to get what's in the power. So this would be d dx of x squared. So I just rewrote this one as this, and I haven't yet differentiated. Cool, cool? All right, so now I'll have minus, and then when I differentiate this guy, what am I going to get? Negative 6x to the negative 2. And then differentiating the arctangent, what's going to happen? I differentiate what's inside that inverse trig function, and that's going to end up being 9x squared over 1 plus the quantity 3x cubed squared. Cool so far? Okay, so now what's going to happen? We will get y prime equals 2/3 times 1 over x minus, differentiating this guy, I'll get 2x, and then plus 6x to the negative 2 minus 9x squared over 1 plus 9x to the 6. All right, so let's clean this up a little bit. We're going to get y prime is equal to 2 over 3x minus 4x over 3 plus 6 over x squared, and then minus 9x squared over 1 plus 9x to the 6. And if we want to just get a common denominator, what do we need? We're going to need, this one will need a 3x squared over 3x squared, that last term. And then the second term is going to need what? Or the second to last, I'm going backwards, my bad. We're going to need a 3 times 1 plus 9x to the 6. So 3 times 1 plus 9x to the 6. And then the second term will need an x squared 1 plus 9x to the 6, that quantity. So we'll have x squared 1 plus 9x to the 6. And then what do we need here? I think we'll need an x times the 1 plus 9x to the 6. So x times 1 plus 9x to the 6. Sorry, it's a little scrunchy. That's what it looks like zoomed up. Just getting a common denominator. So now, let's see what shakes out. We'll get y prime is equal to 2x plus 18x to the 7th minus 4x squared minus, actually that'll be 4x cubed minus 36x to the 9th. And then plus 18 plus 54 x to the 6, and then minus 27 x to the 4th, and that's all over 3x squared times 1 plus 9x to the 6. Cool, cool? And let's see, do we have any common terms? Now, the main thing now would be to just rewrite it in descending order. Descending powers. I mean, you can factor out a 2, but I really don't think that's going to help you. So, y prime would equal to, let's see, negative 36x to the 9th plus 18 x to the 7th plus 54x to the 6th minus 27x to the 4th. And then let's let's see, minus 4x cubed. And then plus 2x plus 18. So let's see, 1, 2, 3, 4, 5, 6, 7 terms. 1, 2, 3, 4, 5, 6, 7. And that's all over 3x squared times quantity 1 plus 9x to the 6. Cool, cool. Getting your algebra warm up and your Calc 1 warm up here. Okay, so now let's take a look at the integration. So here, a couple of things to remember. If you have cosine squared at some angle A, that's equal to 1 minus, or plus rather, cosine at 2A over 2. Sine squared at some A is equal to 1 minus cosine at 2A over 2. Note. So our evil plan here, the first term is not going to be so bad, right? This would end up being 3x cubed when you simplify, and then minus 1/2 times the integral of quantity 1 minus cosine at, when I double 3x, I'll get 6x's with respect to x. And so I'll have 3x cubed minus 1/2 times x minus, so when I integrate the cosine function, I get the sine function, but I'm going to have to, I need a 6 dx, right? I need a 6 here, so I'll have to divide by a 6 to balance it out. And so I'll get minus 1/6 sine at 6x plus our constant of integration. And so cleaning it up, we'll get 3x cubed minus 1/2 x minus, or plus 1/12 times sine at 6x plus our constant of integration. Cool, cool? All right, very good, very good. So now let's check out the next one. We've got the square root of quantity natural log at x with respect to x. So let's rewrite this as the integral of natural log at x to the 1/2 power times 1 over x dx. So here, do you see that, if you recall, the integral of some function at g at x times g prime at x dx gives us a result of an antiderivative evaluated at g at x plus our constant of integration. So here, our g at x has to be that natural log function, right? And g prime at x is equal to 1 over x. So hopefully you see that we have our g prime at x, and then of course we have our dx. So we'll end up getting quantity natural log at x raised to the 3/2, because you got something raised to the 1/2 power, over 3/2, just use the power rule, plus c. If you needed to, you could do a u substitution and that would work too. So that gives us 2/3 times quantity of natural log at x to the 3/2 plus our constant of integration c. And remember, you can't use any kind of property of logs on that because it's the whole natural log function being raised to the 3/2 power. Groovy? All right, so now this one, wow, that looks kind of awful, right? But it's not. It's beautiful because we just get, awesome, 4 times arc sine at x plus our constant of integration. All right, hopefully you feel all warmed up now. Now let's take a look at the definition of the derivative of a vector valued function. Okay, so first let's, before you fill it all in, let's just look at a little bit of a picture of it, all right? So here, if you have, I don't know, let's just make it a little 3D-esque. So this is z, this is y, and this is x. And then you've got your curve, okay? So you've got some curve going like this. See if I went like this, I think it would make it just does a line. Okay, so you've got some curve here. I don't like the hook at the end, sorry. If I do it thicker, I think it works better. All right, so you've got some curve, and then what we have going on is you could have, your vector, right? So let's say we've got this vector here, and we want some r at t vector, okay? So let's say that this vector here, is r, vector r at t. Good so far? All right. Now, let's say that you've got another vector, right, where you're some small change in t away from t, and it's still vector r, all right? So let's suppose that we have now this vector over here, and this vector here is r at t plus delta t. Now, what is this difference going to be if you take a look now at the vector or the distance between these things? I will do it as the vector, right? Between these guys. Okay. That vector there is going to be the vector r at t plus delta t minus the vector r at t. Cool so far? And then r prime at t is going to be the vector that's kissing that curve, right? That begins at the end of our vector here. So r prime at t is this one. R prime at t. Cool so far? All right. So with that in mind, all right, let's just take a look, and we're just using our regular definition of the derivative from before, but we're applying it to vectors. So the vector r prime at t is just going to be, do you guys remember the definition of the derivative? Beautiful. It would be r evaluated at t plus delta t minus r evaluated at t, and again we're dealing with vectors this time, all over that small change in t. Cool so far? All right. So, oh, and what did I forget here? All right, so now let's look at the derivative. So basically, remember that if you had, you know, the slope of the secant line would just be using the definition of the derivative and applying it to our vector valued function, we'd get r prime at t is equal to the limit as delta t approaches 0 of, remember this, r at t plus delta t minus the vector r at t all over delta t. So this is going to be equivalent to r prime at t is equal to the limit as delta t approaches 0 of. Well, we will have f at t plus delta t times I plus g at t plus delta t times j plus h at t plus delta t times k, good so far, and then minus f at t times I plus g at t times j, and then plus h at t times k. Good so far? And all of that stuff is over delta t. But hey, what if we were to get the i's next to each other, right? And the j's next to each other, etc. And you know, factor them out. So let's check it out. So we get r prime at t would be the limit as delta t approaches 0. And then what's going to happen is we're going to have this big quantity, and we're going to have f at t plus delta t minus f at t times the vector I and then what? Beautiful. Plus g at t plus delta t minus g at t times j, and then plus h at t plus delta t minus h at t, and that's times k, and all of that is over delta t. But we know that the limit of a sum is the sum of the limits, correct? So r prime at t could be split to the limit as delta t approaches 0 of f at t plus delta t minus f at t all over delta t, and then plus the limit as delta t approaches 0 of, you got it, g at t plus delta t minus g at t all over delta t, and then finally plus the limit as delta t approaches 0 of h at t plus delta t. Oh, and I'm sorry, I was forgetting my vectors, my bad. We would have our vectors here, I and j. And then this one minus h at t all over delta t times the vector k. But what is that? Well, that gives us r prime at t is equal to f prime at t times I plus g prime at t times j, and then plus h prime at t times k. Isn't that cool? So I did that one in 3D, okay? If you were doing this on the plane, of course you wouldn't have the k. All right, so it turns out that the limit definition for the derivative of a vector-valued function r, like we were working with, is defined as the vector r prime at t equals to the limit as delta t approaches 0 of r evaluated at t plus delta t minus r evaluated at t all over delta t. Good so far? And that's for all t for which the limit exists. If the vector r prime at c exists, then r is differentiable at c. If vector r prime at c exists for all c in an open interval I, then r is differentiable on the open interval I. Differentiability of vector-valued functions can be extended to closed intervals by considering one-sided limits. Okay, so let's take a look at other notation. Right, then, so you did see the r prime at t. There's also d dt of r at t. Can't make my t's today, sorry. And then you can also have this capital D sub t r at t. So depending on, often the class and or the instructor, you'll see different notation. Cool, cool? All right, very good, very good. So now let's go ahead and take a look at this theorem here. Differentiation of vector-valued functions. So if r at t is equal to f at t times I plus g at t times j, where f and g are differentiable functions of t, then it turns out that r prime at t is equal to f prime at t times I plus g prime at t times j. If we're in, that's when we're in the plane, okay? So that's for the plane. And then this one is for space. And it just extends to k. So this is what we showed up here, right? So we used the definition, and this actually would be the proof. The above is the proof for this theorem. Cool, cool? All right. Okay, so then the second one, if r at t is f at t times I plus g at t times j plus h at t times k, where f, g, and h are differentiable functions of t, then r prime at t is going to be f prime at t times I plus g prime at t times j plus h prime at t times k. Higher order derivatives of vector-valued functions are obtained by successive differentiation of each component function. It also turns out that the parameterization of the curve represented by the vector valued function r at t equal to f at t I plus g at t j plus h at t k is smooth on an open interval I if f prime, g prime, and h prime are continuous on I, and the vector r prime at t is not equal to the 0 vector for any value of t on that open interval I. All right? So that gives us, that gives us a lot of options for applications. All right, so properties of the derivative. And these should seem fairly. I didn't spend time to write for us to write them all out. These should seem pretty intuitive to you. So you're just kind of extending the definitions or the properties for regular derivatives to vector valued functions. There is a little bit of a difference though, right? Because remember, there's kind of three ways for us to look at products here, right? So you've got a function, a product. Property 3 is a function at t times a vector valued function at t, and so you use the product rule for that, using f at t as one, and then the vector r at t is the other. When you have a dot product of two vectors at t, then you're going to have the dot product here. Instead of a multiplication of functions, it's the dot product between the vectors, but it still kind of follows that regular product rule for derivatives. And then for cross product, similar deal. All right. So here we go. The 6 represents like the chain rule. And then, of course, if you have a dot product that equals some scalar c, then that a dot product of a vector valued function with itself is some scalar, then it turns out that the dot product of the vector valued function and its derivative is going to be 0. Cool? Okay, so let's go ahead and take a look at some examples. All right, so here we go. Let's find r prime at t dot r double prime at t. Okay, so what is r prime at t going to be? I mean, do you see that we've got a vector in the plane? We have, I'll just do some side work over here. So f at t is equal to t squared plus t. So f prime at t is going to be what? Beautiful, 2t plus 1. And g at t is also equal to, it's t squared minus t. And so g prime at t is equal to 2t minus 1. Cool so far? So what else are we going to need? We're going to need the second derivatives as well, right? So f double prime at t will just be 2, as will g double prime at t will be 2. So let's put it all together. R prime at t is f prime at t I times I, and then plus g prime at t times j. So r prime at t will be equal to, what did we get? 2t plus 1 times I, and then plus 2t minus 1 times j. So we just got these from f prime at t is 2t plus 1. And then g prime at t was 2t minus 1. Good so far? Awesome. So r double prime at t is going to be what? Beautiful. It would be f double prime at t times I plus g double prime at t times j. And what did we get for those? We got, I think, 2 for each of those. So we get 2i plus 2j. And we got those from here. What color? So I'll just do this one. Hopefully it looks different enough. Yep. Cool. All right. Now we want to do their dot product, right? So r prime at t dot r double prime at t is going to be equal to, well, r prime at t was 2t plus 1 times I, and then plus 2t minus 1 times j, dot 2i, because our double prime was 2i plus 2j. Cool so far? Well, putting them in component form, that would end up being what? We'd have 2t plus 1, 2t, I guess I don't need the parentheses here, 2t minus 1, dot 2. And so that would just be 2t plus 1 times 2 plus 2t minus 1 times 2. And that's going to give us 4t plus 2 plus 4t minus 2, which is 8t. Cool so far? All right, so next up, why don't we do this? Let's find the derivative of the cross product here. And so you could find that cross product first, right? But in our properties, what do we know from here? Why don't we apply our formula? So our cross product formula is this one here, right? So let's go ahead and do that one, all right? So here we go. So this one, I'll just write it in general. We would have the derivative with respect to t of this cross product is going to end up being r at t cross u prime at t plus r prime at t cross u at t. Cool so far? All right, so let's take a look. What do we need to do? Well, it might be nice to find the derivatives, right? Find the derivatives. So here with our derivatives for each, okay, because we have r and we have t. So r prime at t is going to end up being what? Beautiful. 1i 2 cosine t at j minus 2 sine t at k. Good so far? U prime at t is going to be negative 1 over t squared times I plus 2 cosine t times j minus 2 cosine t times k. Cool so far? All right. So let's take it's so much easier to take a look at the cross product in terms of and as far as remembering it, in terms of a determinant, right? I hate just memorizing that formula. So R at t cross U prime at t is going to be equal to the determinant, and we'll have our I, our j, and our k, and then for the next line, what are we going to have? You're going to have what R is, and R is t, 2 sine at t, and 2 cosine at t. Move that k over. And then we're going to have, for the bottom row, what are we going to have? Good, we're going to have the components of u prime at t. So u prime at t was negative 1 over t squared. And then, oops, do you see right here? This should have been negative 2 sine at t. So I'll erase it and make it prettier. This should have been minus 2 sine at t. Okay. All right. So we'll have our 2 cosine at t, and then our negative 2 sine at t. Well, if we expand about I, j, and k, right, that's going to end up being the determinant of, so remember you can do like this plus, minus, plus. I'm going to go ahead and put the vectors on the right side. So we're going to have 2 sine at t, 2 cosine at t, 2 cosine at t, and then negative 2 sine at t. And that's going to be times I minus, and then when I expand about j, we'll have the determinant t, 2 cosine t, and then negative 1 over t squared, and then negative 2 sine t, and then plus k, so plus this determinant, and I'll put k on the right. And so when I expand about k rather, I'll have t 2 sine t, so I'll be times k. Sorry, this one was times j. And then negative 1 over t squared, negative 2, positive 2 cosine t. Okay, so then what will we get for that? That will be good. We'll have negative 4 sine squared t minus 4 cosine squared t times I, and then minus negative 2t sine t plus 2 over t squared cosine t times j, and then we'll have plus 2t cosine t minus a minus is plus 2 over t squared times sine t, and that's times k. Now, if you factor out and this ends up getting us, do you see if you factor out a negative 4, you'll have sine squared t plus cosine squared t? So simplifying, we'll have 4i plus 2t sine a t minus 2 over t squared cosine a t. So these two are times j. And then plus 2t cosine t plus 2 over t squared sine t times k. Now, I'll tell you right now that honestly, I don't think this is the easiest way. I think because we have to do a whole nother cross product, right? With r prime at t cross u at t. So honestly, I'm going to say see next page. We've only gotten the first part of it. So this is, fun and all, but I think that I would definitely recommend maybe finding the derivative first and then the cross product. But, that's okay. So now, what are we going to have? We're going to have our next step. We have to do r prime at t cross u at t. So again, we're going to have I, j, and k. And then r prime ended up being, 1, 2 cosine t, and then negative 2 sine t. And then u is just 1 over t, 2 sine t, and 2 cosine t. Cool so far? All right, I'll just work vertically for this one. So again, expanding about the I, j, and the k, because we don't have any zeros in there, we'll end up having 2 cosine t, negative 2 sine t going across, and then we'll have 2 sine t, 2 cosine t. That's going to be times I minus 1 and negative 2 sine t, and then 1 over t, 2 cosine t. This will give us practice on our cross products, right? Times j, and then plus the determinant of 1, 2 cosine t, and then 1 over t, 2 sine t, times k. Groovy? All right, let's see what we get. So this is going to end up being 4 cosine squared t minus minus is plus, so now we'll get 4 sine squared t. Let me double check something, because I needed to factor out here a negative 4. Do you see it'll be a negative to get that identity? Okay, so now we're going to have, this is times I, and then minus 2 cosine t plus 2 over t sine t. That's times j. And then plus 2 sine t minus 2 over t cosine t, and that's all times k. All right, so now that we found the two cross products, remember we're looking here at what we had done, so now we need to add those two results, okay? So, so here we go. We're going to have our see what we had. We had negative 4i, 2t sine t. Negative 4i, and then what did we have? 2t sine t, 2t squared. Right. And then oh no, that one ended up being a plus. No, I didn't. Oh yeah, I did. We have it right. Okay, so then 2t cosine t plus 2 over t squared sine t. And that's times k. Double check. Okay. All right. And now we've got this other one already. So I'm gonna go ahead and add this below. So plus, I'll do it in a purple. Actually, do you see that we'll end up having, this one will be, if I factor out, I can factor out a 4, so I'll get 4i, and then we'll have minus 2 cosine t plus 2 over t sine t times j, and then plus 2 sine t minus 2 over t cosine t times k. So let's put that in there. So we're going to have plus 4i, and then we're going to have minus 2 cosine t plus 2 over t sine t times j, and then plus 2 sine, and that should have been, yeah, it'll just be 2 sine t minus 2 over t 2 over t cosine t times k. And let's group this whole thing, right? Because we're adding that whole thing. And so now let's kind of carouse over here. So our I vectors zero out. And then let's see what we're going to get. We'll just crunch through it and see if we can make it prettier. Negative 2t sine at t plus 2 over t cosine at t. And that's all times j. Actually, let's take care of that other j term as well. We'll have minus 2 cosine t minus 2 over t sine t. And all of this is times j. And then plus 2t cosine t plus 2 over t sine t plus 2 sine t minus 2 over t cosine t, and that's all times k. And let's see if there's anything we can factor out to make it prettier. I don't know that it's going to look all that pretty, frankly. If we go ahead and factor out a negative 2 from the first term, from the j coefficients, then we'll have factor out a sine of t, we will have t 1 over t plus cosine of t, and we'll have one minus 1 over t, and that's all times j. Honestly, I don't know if this makes it any prettier. And then we'll have, if I factor out a positive 2 from this one, we'll end up with factoring out our sine at t term. We will be left with 1 plus 1 over t, and then our cosine at t will be left with t minus 1 over t, and that's all times k. You know what? That's good enough. All right. Sorry it was so messy. Honestly, again, I think it would have been better to take the derivative first and then do the cross product to see, what you get. I think that would be faster. All right. Okay. But anyway, we got to practice our cross products, right? So now let's take a look at the definition of integration of vector valued functions. So if r at t is equal to f at t times I plus g at t times j, where f and g are continuous on the closed interval from a to b, then the indefinite integral antiderivative of r is the integral of r at t dt is equal to the integral of f at t dt times I plus the integral, the quantity, the integral of g at t dt times j. And its definite integral over the interval from a to b inclusive would be the integral from a to b of r at t dt is the integral from a to b of f at t dt times I plus quantity integral a to b g at t dt times j. Good so far? Awesome. So this, of course, refers to the plane. And in space, you've got these conditions here. So we would have the integral of r at t dt would be quantity f at t, integral f at t dt times I plus quantity integral g at t dt times j plus quantity integral h at t dt times k. And, of course, our definite integral from a to b in space would be this. So the integral from a to b, f at t dt times I plus integral from a to b g at t with respect to t times j plus the integral from a to b h at t dt times k. And this is for space. Groovy? All right. So now let's take a look. Evaluate the indefinite integral, right? So remember, all we're doing is we're integrating each of these functions with respect to t. Now here, if you're going to add some kind of constant of integration, it would end up being a vector. Okay, so just be careful on that. So let's kind of go back and take a look at this example. So for this one, what's going to happen? We're going to get the integral of 4t cubed dt times I plus the integral 6t dt times j minus the integral of 4t to the 1/2 dt times k. All right, well, what are we going to get for this one? So this would be, I believe, just t to the 4th times I, and then plus 6t squared over 2 would be 3t squared times j, and then minus, what would we get, 4 times t to the 3/2 over 3/2 times k plus our vector constant of integration. And cleaning it up, we will have t to the 4th times I plus 3t squared times j minus 8/3 t to the 3/2 times k. Good so far? So basically what's going to be happening is you could have added a constant to each vector, right? Like plus a sum c1 times I plus some c2 plus some c3. But instead that makes, a vector of constants. And so that's why we're just going to say plus c. All right, at the end. And remember, it's a vector c. And I forgot to put that. My bad. All right. Next step, we'll do and evaluate a definite integral. Okay, so here I'm just going to go a little bit faster because I think you guys know these antiderivatives, hopefully. So this is going to end up being, when I integrate secant t tangent t, do you see that I get secant at t? And that's going to be from t equals 0 to pi over 4. And we're going to multiply that to I, right? And then the derivative of tangent at t is negative natural log cosine at t, right? And so that'll be evaluated from t equals 0 to t equals pi over 4. And that cosine at t is an absolute value. And that's all times our j. And then 2 times sine t at cosine t. Well, for that one, remember, if your g at t was equal to sine t, g prime at t is equal to cosine at t. And so that's how I'm going to look at that one. So we'll end up getting plus, you'd have 2 sine squared at t over 2. So that would just be sine squared at t, evaluated from t is 0 to t is pi over 4. And that's times k. All right, so let's see what we get. So this would end up being secant at pi over 4 is, good, root 2. So I think we get root 2. And secant at 0 is, whoops. So we'd have minus 1, and that's times I, minus, so cosine, absolute cosine at pi over 4 is root 2, so we'd have natural log root 2. And then, oops, natural log root 2 over 2, or 1 over root 2, whatever you prefer. And absolute value of root 2 over 2 is just root 2 over 2. And then minus natural log at 0, right? Or natural log at 1, sorry. And then lastly, we would have sine squared at t. Well, when sine is at pi over 4, you could think of it as 1 over root 2, so you'd end up with a half, and then minus 0, right, times k. So cleaning it up, let's see what we get. So we'll have root 2 minus 1 times I, and then minus natural log at root 2 over 2 times j. There's a j here. And remember, natural log of 1 is 0. and then plus 1/2 times k. Now notice, when you do the definite integral, you get constant coefficients to the vectors I, j, and k. And when you do the indefinite, we got variable coefficients. Groovy? All right. And that ties it up for today. All right. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.